Welcome to this deep dive. Today, we're really unpacking something kind of wild. It's the invisible infrastructure that keeps our global food supply alive.
Yeah, and it's a lot more complex than you might think.
Oh, absolutely. We're pulling from just a single source today, which is this highly specific, very technical diagnostic manual for refrigerated transport units.
Right, and our mission for this deep dive is to basically decode just one critical alert from that manual.
Yeah, alarm code 29, which is check defrost damper circuit.
I know. It sounds like just a hyper niche piece of engineering jargon.
It really does. Like, why should you care about a damper circuit, right?
Exactly. But analyzing this single alarm code actually reveals this brilliant piece of technological detective work.
Yeah, you really get to see the microscopic logic gates and like the mechanical guardrails that prevent catastrophic temperature failures.
Yeah, because we're talking about transporting highly sensitive perishables and pharmaceuticals here.
Exactly. We're essentially looking at how a mobile refrigeration ecosystem manages its own immune system.
That's a great way to put it. An immune system.
Right. So to really grasp what alarm code 29 is telling you kind of have to start with the physical reality of the hardware.
Yeah, you have to picture the actual truck.
So the text places this defrost damper directly in what it calls the discharge airstream.
Right, because the refrigeration unit on a trailer operates essentially as this massive thermal lung.
A thermal lung, I like that.
Yeah, it continuously pulls ambient air from inside the trailer, right? It cools it over a set of evaporator coils and then blows that chilled air back out over the payload.
And that outward flow, that's the discharge airstream.
Precisely.
Okay, so the text specifies that the damper is closed during defrost to prevent warm air from being circulated over the load.
Right, which is so important.
Yeah, because if you're tracking the thermodynamics of this whole mobile refrigeration cycle, this is addressing the inherent paradox of the system.
The ice buildup.
Exactly. Pulling moisture out of the air and running it over sub-zero coils, it inevitably builds up frost.
Always. You can't avoid it.
And if you let that frost accumulate, it just insulates the coils, choking the unit's ability to transfer heat.
Right. So the unit has to periodically force itself into a defrost cycle.
Which seems so counterintuitive.
It does. It often uses hot gas bypass from the compressor or even electric heating elements just to melt that ice off its own internal coils.
So you are intentionally generating a massive thermal spike inside a cabinet whose sole purpose is to keep things freezing cold.
Exactly. It's wild when you think about it.
But you absolutely cannot let that thermal spike wash over, say, a payload of sensitive biologics or fresh produce.
No, that would ruin everything.
Right. So the damper acts as this thermal airlock. Basically, it's like a nightclub bouncer for air.
A bouncer for air. Yeah, that's exactly what it is.
Right. Like when the unit initiates its internal maintenance cycle, this bouncer just slams the door shut on the discharge plenum.
It completely isolates the cargo area from the destructive heat of that defrost cycle.
Okay, so that's the physical door.
Well,
but how does it move?
Well, the mechanical actuation of that door is driven by the damper solenoid.
Right, and the text notes the solenoid is mounted just outside the discharge plenum, and it connects to the damper door via a mechanical linkage.
Yeah.
When you apply power to that solenoid, the electromagnetic field pulls a rod, actuating the linkage and forcing that heavy damper door shut.
Right. But that physical action hinges entirely on the electrical command structure.
The nervous system.
Yeah, the nervous system. The source breaks down the anatomy of this specific circuit. It's a 2-wire circuit powered by a 12 VDC supply.
That's direct current, right?
Yep, 12 volts direct current. And the power routing is tightly controlled by the interface board.
Okay, let's talk about the interface board. The manual specifically mentions relay K4 and fuse F6, which is a 15-amp fuse.
Right. The interface board acts as the primary logic controller for the whole cooling unit.
The brain.
Yes, the brain. So when the microprocessor dictates that a defrost cycle is required, it commands relay K4 to close.
And that sends your 12 volts down a specific wire labeled the 29 wire to the positive side of the damper solenoid.
Exactly.
And then the text identifies the CHD wire connecting the opposite side of the solenoid to chassis ground at the ground plate, which completes the loop.
Right, and both of these are routed together through the trailer's main harness.
Which is a pretty harsh environment for wires.
Oh, incredibly harsh. You're dealing with very long wire runs through an environment subject to constant vibration, extreme thermal cycling, moisture, you name it.
Wow.
Yeah. The main harness is the central nervous system, and routing the ground all the way back to a dedicated ground plate rather than just relying on like a localized chassis ground screw that minimizes the risk of resistance buildup from corrosion.
That makes total sense. But I actually want to push back on a specific contradiction I noticed in the manual's wiring instructions.
Oh, really? Which part?
So the source explicitly states that the solenoid itself is not polarity sensitive.
Right.
Because it's an inductive coil, right? Regardless of which way the current flows, it generates the magnetic field needed to pull the mechanical linkage.
That's correct.
But then, in the exact same sentence, it mandates that the suppression diode must be installed with the bar end of the diode toward the 29 wire.
Ah, yes.
Wait, if the primary load, the solenoid doesn't care about polarity, why is there a strict directional mandate for installing this diode?
Okay, so that is a textbook application of managing flyback voltage.
Flyback voltage.
Yeah, you have a heavy inductive load in the solenoid. When the interface board cuts the power, when relay K4 opens, the magnetic field that was supporting that solenoid coil collapses instantly.
Oh, right. By Faraday's law of induction, that collapsing magnetic field is going to induce a massive voltage spike in the opposite direction.
Exactly. A transient voltage spike that can easily exceed hundreds of volts.
Oh, hundreds of volts from a 12-volt system.
Yeah, and if that energy travels back up the 29 wire, it will hit the interface board and instantly destroy those sensitive solid-state logic components.
Oh, man, so it just fries the brain.
Totally fries it. So the suppression diode is installed in parallel with the solenoid coil.
Acting like a one-way valve.
Precisely. By orienting the bar end, the cathode, toward the positive 29 wire, the diode remains reverse biased during normal operation.
Meaning it essentially does nothing while the door's shut.
Right. But the millisecond relay K4 opens, and that negative to positive voltage spike flies backward.
The diode becomes forward biased.
Exactly. It provides an immediate low resistance path for that high voltage transient to loop safely back into the solenoid coil and just dissipate as harmless thermal energy.
It just clamps the flyback voltage locally. That's so elegant.
It really is. It's electrical armor for the logic board.
Okay, so all of this electrical armor protects the logic board, but the system still needs to know if the physical door is actually functioning right.
Right. Which moves us into the system's localized intelligence. The pre-trip test.
Yeah, this is where the truck interrogates its own circuitry before it ever allows the unit to clear for dispatch.
It's checking its own vitals.
Exactly. And the course material outlines 3 very specific logic gates, the computer monitors to set alarm con 29.
Let's start with condition 1.
Okay, so condition 1. The system energizes the damper solenoid. It's looking for the current to fall within a specific window of 2 to 10 amps.
Right.
And if it doesn't, it throws a check alarm.
Diagnostically, that 2 to 10 amp window tells you everything about the health of the circuit.
How so?
Well, if you're drawing less than 2 amps, you have a high resistance fault. That could be like a corroded pin in the main harness, a failing relay contact, or even a degraded winding in the solenoid itself.
Okay. And conversely, I guess pulling more than 10 amps means you're approaching a short-to-ground scenario.
Exactly. Or the mechanical linkage is severely binding, and the coil is drawing maximum locked rotor current, just trying to force a jammed door shut.
Wow. So either way, the system flags it.
Yeah, it throws that check alarm. But condition 2 is where the microprocessor forces an immediate hard stop.
Condition 2 tests the de-energized state.
Right. The system opens relay K4, cutting the power. If the current does not drop back down to less than or equal to 0.5 amps.
It triggers alarm code 29, but this time it's a shutdown alarm. The unit physically locks out and refuses to run.
And the distinction between a check alarm and a shutdown alarm is so critical here.
It's kind of like the difference between a check engine light and your engine physically turning itself off.
That's a perfect analogy. A check alarm is essentially a telemetry flag. The resistance is out of spec, sure, but the unit can theoretically still regulate temperature.
But a shutdown alarm under condition 2 means you have leakage current flowing when the circuit should be completely dead.
Right. If you have current flowing in a de-energized state, it means the K4 relay might be welded shut or there's a short to power in the harness somewhere.
Meaning the solenoid is stuck on.
Yes.
And if the solenoid is permanently engaged, the damper door is permanently closed.
Exactly. And think about what that means. If the logic controller tries to drop back into a standard cooling cycle, it's going to blow sub-zero air against a sealed thermal airlock.
Wait, so 100% of your airflow is blocked?
100%. The cold air backs up into the evaporator cabinet, the system will likely trip on a high-pressure fault, and absolutely zero cooling will reach the payload.
Oh, wow. So it completely neutralizes the entire purpose of the transport unit.
It's a fatal error for the cargo, so the system preemptively shuts down to force human intervention before the payload actually degrades.
That is amazing. And the engineers also accounted for hardware variations, right?
Yeah, they had to.
Which brings us to condition 3. This addresses units equipped with a damper gear motor instead of that fast-acting solenoid.
Right, because a gear motor slowly cranks the door open and close over several seconds, rather than just snapping it shut.
So condition 3 states, if the motor's travel timer exceeds its limit without hitting the motor stall current, it triggers a check alarm.
Using a motor stall current as a proxy for physical closure is just a highly ruggedized engineering solution.
A proxy, meaning they don't actually have a sensor on the door.
Exactly. Think about it. In a discharge plenum that's constantly oscillating between deep freeze and hot gas defrost, physical limit switches or optical sensors are incredibly prone to icing up and failing.
Oh, of course. A delicate sensor would just break or freeze over.
Yeah. So instead of relying on a fragile sensor to confirm the door is shut, the controller just watches the electrical amperage.
That is so smart. It knows the motor should take, what, roughly 5 seconds to swing the door.
Around there, yeah. And when the door physically hits the frame, the motor binds. It literally can't turn anymore.
Which causes the electrical current to instantly spike.
Right. That spike is the stall current. The logic board senses that exact amperage peak and immediately cuts the power, knowing the door is mechanically sealed.
But if the microprocessor's internal stopwatch runs out before it ever sees that amperage spike,
Then it means the motor just kept spinning freely.
like the mechanical linkage snapped or the gear teeth sheared off or something.
Exactly. The board knows the electrical circuit is intact, but the mechanical action obviously failed, so it throws the flag.
Okay, so once that flag is thrown, whether it's a check or a shutdown alarm, a human has to actually fix it.
Yeah, a technician has to interface with the unit.
And the source details an 8-step diagnostic procedure. Step 1 dictates that the alarm must be cleared manually.
Right. The system will not auto-reset a critical airflow fault. You have to physically acknowledge it.
And the run relay must be energized to provide testing power to the circuits.
That's right. And step 2 is where the diagnostic process moves from just basic troubleshooting into real forensic data analysis.
Yeah, the technician is instructed to download the Service Watch data logger using a proprietary software called WinTrack.
At the technician user level.
Right, they aren't just reading a generic fault code.
No, not at all. Service Watch logs the exact telemetry of the unit at the exact millisecond the alarm triggered.
Wow.
Yeah, you can pull the WinTrack report and see the ambient temperature, the coil temperature, the exact voltage drop across the K4 relay.
And the real-time amperage draw that caused the logic board to flag the error in the first place.
Exactly. It completely eliminates the guesswork of intermittent failures.
Because intermittent failures are the worst.
A total nightmare for mechanics.
So once they have the telemetry, they run localized physical tests. Using the interface board test mode, they attempt to fire the damper circuit manually.
And they're instructed to watch for LED 4 to illuminate, specifically for Zone 1.
What does LED 4 tell them?
LED 4 verifies the logic side of the circuit. If that diode lights up, you know the microprocessor is successfully commanding the K4 relay to close.
The brain is communicating.
Exactly. Next, you have to verify the physical circuit.
Right. Step 6 has the technician use the truck premium display's built-in amps gauge to measure the actual current draw of the solenoid while it's being forced in test mode.
And the manual provides a very specific benchmark here. A healthy damper solenoid should draw approximately 6 amps.
Which perfectly aligns with the parameters of the pre-trip test we talked about earlier.
Right. The logic board wants to see between 2 and 10 amps. So a 6 amp draw puts you dead center in the nominal operating range.
Okay, but what if LED 4 is lighting up, but you aren't seeing that 6 amp draw on the display?
Then you move to step 7. This is the definitive isolation test.
The technician energizes the circuit and uses a multimeter to check for battery voltage, specifically on the 29 circuit wire down at the solenoid itself.
Yeah. And if you read a nominal 12 volts at the component, you have just verified that the interface board, the K4 relay, the F6 fuse, and the entire length of the 29 wire in the main harness are performing flawlessly.
The potential energy is arriving exactly where it needs to be.
Exactly.
It's basically a plumbing analogy, right? Voltage is like water pressure, and current is the actual water flowing.
That's a really good way to visualize it.
Yeah, so if you have pressure pushing, meaning voltage on the 29 circuit, but no water is coming out of the faucet, meaning zero current.
Then you know immediately what the failure is. Your valve is totally jammed.
The internal coil winding of the solenoid is open.
Right. The wire inside the electromagnet has physically snapped.
The circuit is literally broken inside the component housing.
Yes. So you replace the damper solenoid assembly, clear the codes, and the unit is ready for dispatch.
It is a highly elegant diagnostic tree. It isolates the microprocessor logic, it isolates the harness integrity, and it isolates the terminal component.
It's brilliant. But the manual does leave one final, really crucial caveat at step 8.
Oh, right. The trap for the unwary technician.
Yeah, regarding software configuration.
If a technician previously replaced the interface board or, flashed the firmware but failed to configure the parameters correctly in the software,
the unit might not throw alarm code 29 at all.
Wait, really? What does it throw instead?
It might throw alarm code 137, check damper motor heater output.
Wow. Which is completely different.
Entirely different. This really highlights the vulnerability of complex hardware-software integration.
Yeah, because if the firmware is configured for a different zone setup, the logic controller expects to see the resistance of a damper motor heater.
Instead of the inductive load of a solenoid?
Right. So when it runs the pre-trip test, the amperage feedback doesn't match its configuration tables, so it just throws a completely irrelevant code.
Exactly. You could have a technician spending hours tearing apart the discharge plenum, replacing relays, and chasing phantom wiring faults.
For a heater that doesn't physically exist.
Right, all because a drop-down menu in the WinTrack software wasn't updated during a previous service interval.
That is wild. The hardware and the firmware have to be in perfect alignment for the diagnostic logic to actually function.
It's a stark reminder of how deeply intertwined the digital and mechanical systems are in modern logistics.
It really is. I mean, we've taken a deep dive into just a few paragraphs of a proprietary diagnostic manual today.
Just a tiny excerpt.
But within those pages, you see the entire journey from a solid-state logic gate commanding a 12-volt relay to a flyback diode protecting the circuit to a heavy mechanical door physically blocking the thermodynamics of a defrost cycle.
It completely reframes the scale of engineering operating quietly in the background of our infrastructure,
Absolutely. The reliability of these units isn't an accident.
No, it's the result of aggressive, automated self-interrogation happening constantly.
So the next time you see perfectly unblemished produce or, temperature-sensitive medications safely delivered at the store, realize the sheer volume of hidden telemetry making that possible.
Yeah.
You literally have 15 amp fuses, motor sol current proxies, and automated pre-trip sequences, exactly like the ones governing alarm code 29 to thank for it.
And that actually leads to a fascinating broader implication, I think.
Oh, what's that?
Well, think about those service watch data loggers we talked about.
Right, the telemetry logs.
Yeah. You have millions of transport vehicles globally running these automated, localized pre-trip tests every single day.
Millions of them.
Exactly. And they are logging high-resistance faults, localized temperature anomalies, voltage drops, everything.
Okay, I see where you're going with this.
If you could aggregate that specific telemetry across the entire global grid in real time, you wouldn't just be fixing broken trucks.
Wow. You could build a predictive failure model for the entire human supply chain.
Yes. You could map out thermal degradation and component failure before the payload ever even reaches the loading dock.
It's like a massive invisible nervous system.
Yeah.
Keeping the modern world fed and supplied.
Exactly.
That's incredible. Something to keep in mind the next time you look at the complexities of the logistics network.
Definitely.
Well, that does it for our deep dive today. Thanks for joining us as we unpack the hidden world of alarm code 29.